You know, whenever you see a survey or a poll, you have to wonder, how accurate is it really? Well, what if I told you there's a statistical technique that can make your data more accurate, not by changing how you sample, but by cleverly adjusting it after you've already collected everything? That's what we're talking about today. We're diving into a powerful tool called post-stratification.
All right, here's our game plan. We're going to start with what post-stratification even is. Then we'll get into the mechanics, the formulas behind the magic. After that, we'll walk through a real-world example to see how it works in practice. And finally, we'll put it all in context with some other methods so you know exactly when to use it.
So first things first, what exactly are we talking about here? In a nutshell, it's the art of stratifying after you've already done your sampling. Okay, so here's the core idea. Post-stratification is what you do in the analysis phase. You take your sample data and you adjust it using known facts about the population, things you might get from, say, the census. It's like you've taken a photo and now you're using Photoshop to correct the colors to make it look more true to life. It's not part of the initial design, it's a correction you apply at the end.
Now, it's super important not to confuse this with regular stratification. Think of it this way. With stratification, you're an architect. You design the survey from the ground up, deciding ahead of time, I'm going to survey 100 people from the north, 100 from the south. You fix those numbers. But with post-stratification, you just cast a wide net, like a simple random sample. Then you look at what you caught and realize, I got 120 people from the north and only 80 from the south by pure chance. The key difference is that the sample size in each group is random. It's not fixed by you.
So that brings up a pretty obvious question, right? If you could just stratify in the first place, why wouldn't you? Why wait until after? Well, a lot of the time you just don't have the information you need up front. Your sampling frame, that's the list of everyone you could possibly sample, might just be a list of names or phone numbers. You can't stratify a phone survey by gender if you don't know the gender of the person you're about to call. So you do the next best thing. You call a random sample of people, you ask their gender during the survey, and then you adjust your final numbers to make sure the gender breakdown in your analysis matches what you know the true population looks like. Okay, now that we've got the what and the why, let's pop the hood and look at the engine. Let's talk about the formulas that make this all work. I know, formulas can look a little intense, but this one is actually beautiful in its simplicity. All it's doing is creating a weighted average. That NHN part, that's just the true proportion of a group in the population. The YH, that's the average you found for that group in your sample. So if your sample accidentally got way too many young people, this formula says, okay, take the average for young people, but weight it by their actual smaller share of the population. It corrects the imbalance. And now for the variance. Here's the really cool part. This formula for the variance of our post-stratified estimate looks almost exactly like the one you'd use for a proportionally stratified sample. What does that mean? It means by doing this adjustment after the fact, you get almost all the same benefits of precision as if you had done the more complicated and often more expensive stratified design from the very beginning. That's a huge win. Now, if those formulas are a bit much, don't worry. There's a much more intuitive way to think about this. And it's actually how it's done in practice, by adjusting weights. Just imagine every person in your sample has a vote. We're just going to make some votes count a little more and some count a little less to make the whole group a perfect mirror of the population. And this is how we do it. Look at that formula. The Y is the original weight. Maybe every person counts as 1. The magic is in that fraction, NH over NH. NH is the true size of a group. NH is what our sample thinks the size is. So if we undersampled men, the true number, NH, will be bigger than our sample's estimate, NH. That fraction will be greater than 1 and will upweight every man in the sample. If we oversampled women, that fraction is less than 1 and we downweight them. It's just a correction factor. Okay, enough theory. Let's get our hands dirty with a real example. This is where it'll all click into place. So here's the scenario. We've got an SRS of 300 counties out of about 3,000 in the US. We want to estimate something about agriculture. But, oops, we forgot to stratify by region, and we know regions are really different. The good news is, we know from the census exactly how many counties are in each region. We can use that information to fix our estimate. This table lays it all out for us. NH is the ground truth, the actual number of counties in each region. NH is what our random sample happened to give us. As you can see, the numbers aren't perfectly proportional. Our job is to use the other columns to calculate that final column, WI, the new smarter weight for each region. Let's just walk through one of these for the Northeast.
The original weight for any county was just the total population divided by the sample size, so 10.26. Now we got 24 counties from the Northeast in our sample. Based on that original weight, our sample estimates there are about 246 counties there. But we know the truth. The real number is 220, so we divide the true number by our estimate and multiply by the original weight. Since we oversampled the Northeast, the new weight is smaller. We're dialing down its influence.
And this quote just says it all perfectly. We're correcting for the quirks of random chance. The sample happened to grab a few too many Northeast counties, so we give each of them a slightly smaller voice in the final calculation. And if you look at the table for the South and West, where we got too few counties, their weights are adjusted up. It's a beautiful rebalancing act. So after we do all this reweighting and run our analysis again, we get a new standard error for our estimate. And that new improved number is 17,443. And here is the payoff. This is why we did all that work. The original standard error from our simple random sample was almost $19,000. By applying post-stratification, we knocked that down to about 17,400. We've made our estimate more precise, and the best part? We didn't have to collect any more data. We just used information that was already out there. That is seriously efficient. Okay, let's zoom out. It turns out post-stratification isn't some weird standalone trick. It's actually part of a larger family of techniques called ratio estimation. Let's see how it fits in. When you're working with stratified data, you basically have two choices for ratio estimation. The combined estimator mushes all your strata together first and calculates one single overall ratio. The separate estimator is a bit more nuanced. It calculates a specific ratio for each stratum first and then combines those results. And here's the big connection. Post-stratification is really just a special case of the separate ratio estimator. Think about it. In our county example, we didn't calculate one correction factor for the whole country. We calculated a separate one for the Northeast, a separate one for the North Central, and so on. Understanding this link helps us know when post-stratification is the right tool for the job.
So this gives us options, which is great, but it also means we have to make a choice. How do you decide which estimator to use? Here's the basic trade-off. The separate estimator, which includes post-stratification, is the powerhouse. It's more efficient and precise if the thing you're studying is truly different across your groups. But it has a weakness. You need a good number of data points in each and every group. If some of your NH values are really small, the separate estimator can get biased. The combined estimator is the safer, more stable option in that case. It has less bias when sample sizes are small, but you might lose some precision because you're averaging everything out. So, to wrap it all up, post-stratification is a testament to being a smart data analyst. It's about using all the information available to you, not just the data you collected. Which leaves us with this final thought. If we can use things like region, or age, or gender from the census, what else is out there? What other known truths about the world could we be using to make our estimates even better? That's where the real creativity begins.